You ever see an athlete, a dancer, or yeah, even a superhero, and just think, how on earth do they do that? How does a body pull off those insane feats of coordination, balance, and just perfect timing? Well, the secret isn't in the muscles. It's in a part of the brain that's a total unsung hero. Today, we're taking a look inside that secret command center.
I mean, seriously, picture it. Swinging through a city, letting go at the perfect millisecond, catching the next web, all while accounting for wind speed and landing on a tiny little flagpole. It looks impossible, right? But the gear that makes it happen, the biological hardware, it's not science fiction. It's in all of us. So what exactly is running the show?
Okay, so to really get how this command center works its magic, first we need a map. You gotta know the layout of the headquarters before you can understand the operation. So let's start with the basic anatomy.
And there it is. See that? Tucked away at the back and bottom of the brain, right underneath the main event. That's the cerebellum. The name actually means little brain in Latin, which is pretty spot on. Its whole mission is to make sure every move you make is smooth, coordinated, and on target.
Now, if you look closer, you'll see that just like the big cerebrum up top, the cerebellum is split right down the middle. It's got two halves, a left and a right side, that we call the cerebellar hemispheres. And you guessed it, they've got to work together.
So how do they stay in sync? Well, they're connected by this thing right in the center called the vermis. And vermis is just Latin for worm, which, yeah, it kind of looks like one. Think of it as the main data cable connecting the left and right sides, making sure they're always on the same page.
All right, to make it easier to see what's what, scientists sometimes imagine it unrolled, kind of like a scroll. And when you do that, you can clearly see three main sections or lobes. You've got the anterior lobe up front, the big posterior lobe in the middle, and then that tiny little flocculonodular lobe down at the bottom. So that's our basic map.
So we've got the map of the headquarters, but a map doesn't tell you who does what, right? The cerebellum isn't just one big blob. It's split into three functional zones, and each one has a very, very specific job. It's time to meet the specialists.
First up, the vestibulocerebellum. Functionally, this is that little flocculonodular lobe we just saw. Its whole deal is balance and coordinating eye movements. This is what lets you, or, a certain hero, balance on a skyscraper ledge without even thinking about it. It's what keeps your eyes locked on a target even when you're flipping through the air. It's basically your body's built-in gyroscope.
Next, we have the spinocerebellum. This zone covers that central vermis and the areas right next to it. Its job? Motor execution. This is the part that's actually controlling the precise movements of your arms, your legs, and even your core muscles. This is the system that makes sure when you reach out to grab something, your hand goes exactly where it's supposed to, with just the right amount of speed and force.
And finally, the biggest zone of all, the cerebrocerebellum. This is made up of those large outer hemispheres. Think of this as the master planner, the strategist. Before you even begin a complex series of moves, this part is already planning and programming the entire sequence. It's like looking at the entire city skyline and mapping out the perfect route from point A to point B before you even take that first jump. Okay, so we have a zone for balance, a zone for execution, and a zone for planning. But here's the big question. How does it all get better? Nobody's perfect on the first try. So how do we go from a clumsy first attempt to a smooth, automatic, perfect movement? Well, that is where the cerebellum's amazing learning circuitry kicks in.
The cerebellum is constantly getting two different kinds of intel. First, you've got mossy fibers. Think of these as a constant status update. They're bringing in general motor commands and sensory feedback from all over the body. It's the background chatter. Then you have the climbing fibers. These guys are the specialists. They don't talk much, but when they do, everyone listens. They fire a single, powerful signal, and they only do it when a movement is wrong. They are, literally, the error signal. Now, these two signals work together through a brilliant process called long-term depression. And let me be clear, this has absolutely nothing to do with feeling sad. In neuroscience, depression just means to weaken something. So when a climbing fiber sends that error signal, right as a mossy fiber delivers a bad command, the brain turns down the volume on that specific bad connection. It teaches the nerve cells to listen a little less to that faulty command next time. This is, at the cellular level, how we learn from our mistakes.
So, let's walk through it. Step 1. You try a new move. The initial command goes through the mossy fibers. Step 2. The move isn't quite right. Maybe you overshoot the landing. It's imperfect. Step 3. That mistake triggers the climbing fibers, which blast out a powerful error signal. And step 4. That error signal weakens the exact connection that caused the mistake. The result?
The next time you try, your brain is already steering you away from that error. You get a little bit better. Now, do that a few thousand times, and practice starts to look a whole lot like perfection.
Now, all this information, all this learning has to get sent back out. The cerebellum does this through 4 pairs of crucial output stations called the deep cerebellar nuclei. It sounds complicated, I know, but my mentor back in med school taught me a super simple, if a little unhealthy, way to remember them all.
You ready? It's don't eat greasy foods. Yeah, I know, it's silly, but I promise you, from this day forward, you are never, ever going to forget the names of the deep cerebellar nuclei.
Let's break it down real quick. Don't is for the dentate nucleus, the biggest one that handles the output for movement planning. Eat and greasy are for the emboliform and globose nuclei. They work together to send out the signals for motor execution. And foods stands for the fastigial nucleus, which handles all the output for balance. Each one is a critical pipeline out of the cerebellum.
So this whole system is just an incredible piece of biological engineering, right? It's amazing. But what happens when it gets damaged? What happens when this finely tuned network goes down? Because seeing what goes wrong really drives home just how much the cerebellum does right. And because those zones we talked about are so specialized, where the damage happens makes a huge difference. If there's a problem right down the midline, in the vermis or the flocculonodular lobe, the balance zones, you get an unsteady, staggering walk called truncal ataxia, plus issues with eye movement. But if the damage is out to the sides, in the hemispheres that control the limbs, you get what's called appendicular ataxia, major incoordination of your arms and legs.
And that really brings it all back home. The cerebellum's incredible gift of smooth, planned, error-corrected movement, it's not just for swinging between buildings. It's for walking down the street without stumbling. It's for picking up a coffee cup without spilling it all over yourself. It's the silent partner in almost everything you do every single day.
So from the grand plan to the tiniest correction, from learning from every single slip-up, the cerebellum is what turns your practice into perfection. So I'll just leave you with this to think about. What new skill is your little brain working on and mastering right now?